Embeddings in machine learning. Embedding is a task-specific lower dimensional vector representation of data like word, image, document, or an user. Hello, so this is another video. Welcome back. Happy that you are interested. And so this video is about vector representations, which are specially designed to for specific task. And this is something that's super important in machine learning. It has a long history and something you should definitely know if you are not aware, and maybe you can learn also something new by reviewing this quickly once more again. So let's say we want to represent our data. That's always what we want to do, because we want to represent our data such that we can compute our tasks on computer. And we start with simple high-dimensional feature vectors. So we start with something super simple that exactly represents our data. For example, we can have a text and split it into words, and then use a word index for each word. So that's very high dimensional because there's 10,000 words, for example, 100,000 words. But it's something that we can easily convert to numbers. There are other ways to do this. And then we find the lower dimensional vectors that are optimized for our tasks. And these are called then embedding representation. They represent pieces of our data or the entire data piece. So these are called embeddings. These are vectors in some vector space. What are common training tasks for these sort of embeddings? These are often, these can be supervised, unsupervised. And for example, we can have are these two images similar? This is, for example, used for teacher-student architectures. Or how similar is this image to this abstract product image class, right? So that's, for example, in image text classification, for which I have a blog post as well. It's over here. Multimodal image text classification, and I did a video before. I will share a link in the notes. So what we usually do is that before we represent the entire data, we often split the data into smaller pieces, into some meaningful parts, and that are sometimes called tokens, not every time. So if we do tokenization, how what it means. I have a specific page for it. You can read more about it here. It's used in natural language processing. It's used in images as well. But regarding the embedding, tokenization is just cutting the input data into meaningful parts that can then be represented or embedded into a vector space. So we get the embeddings for individual parts in the input data. For example, image can be split into patches, text is split into tokens. For example, some sort of frequent words, and maybe we don't look at the non-frequent one. You can read more about tokenization in Transformer clicking on this link here. And because we did this split of the input, in case of the tokenization, maybe we also need to add the positional embedding. And then we need to say where the token was in the input. And how do we embed those tokens? So for example, in case of the natural language processing, we map, for example, words, tokens to their vector representations, or image patches to those vectors as well, to embeddings. And once we have these tokens embedded, we still want the final representation. We want the full contextual representation. And so that means that within the architecture, usually we pull the sequences of embeddings, and then in various ways, like averaging or maximum, and then we get the full contextual representation. So going from the historical perspective, initially when the computer science was starting, we basically replaced the libraries of paper documents with databases of some textual representation of those documents. And there were first requirements, first features that needed to be developed, like we wanted to search in the database, we wanted to find some topics that are stored in the database, and these kind of methods. So for those, there were many ways, many new ways how to do them, and usually those used some sparse matrices. So you can read a bit about sparse matrices here on this link. For example, and the sparse matrices where, for example, you just count the occurrences of words in the document, and those create these feature vectors that are very, very high dimension, but I can still do some useful things with them. I can, for example, do this term frequency, inverse document frequency, or latent semantics analysis. And these two approaches basically use these counts of words in the documents, such that I can, for example, cluster documents that are about the similar thing, or I can, when I write a query, I can actually weight which words are sort of more relevant for the search, and I can sort the document so I can improve my search. I will probably write a post about this as well in the future. And later, this co-occurrence of words in documents was also used for embedding of the words. But here we created the document representations, and that's where we started. Once we were okay with the document representations, well, those were easy enough for people to do, then the contextual word representations, which required more computational resources, were possible to do over time, like in 90s or so. And basically we split the document into some sentence sizes and words, and then we could try to represent each word as a vector in some smaller space, for example 300 dimensions. And because initially the word was represented as where it exists in the vocabulary, we can now represent it as in 300 dimensions. So it was 10K vocabulary feature vectors, and we compressed it down to 300. So while these taken dimensional vectors were sparse, we embedded them now into some dense vectors, and as well we always limit the norm. So basically, as well, the embeddings are really close together because there's lots of them. 10K in the vocabulary words are suddenly compressed into less dimensions and less space because the norms are limited. The vectors cannot grow too much. I will put a link on vector norms in fast text and Word2Vec here as well. And so these methods for embedding of the words can now help us to represent words as a vector. So for example, here you can see in the 3 dimensions, I have this using this viewer in TensorFlow. You can see the words represented in 3 dimensions, for example. But usually it's more 300. So one of the first methods was Word2Vec, and again this represented each word without the specific context. Like each word had some vector in 300 dimensions, so the context wasn't. The context was completely general across all the documents. How did it work again? So I create a window of 10 surrounding words, something like a sentence size, and I want yeah, you can have a look at this. So I have this sentence size, and I have this word here that I want to represent. And how do I represent this word? So I basically pretend that I don't know it. I represent all other words, and I sum up their vectors, and then I require that vector to be close to my word that I, that I pretend that I don't see. And if I do this, I can actually really mask the word, and because if I'm successful and if the sums actually are close to the vector of the word, then I can actually even predict the word. So, but again, this is a training procedure. You have this running window of 10 words, and you train the sum of the vector representations of the embeddings of those surrounding words. You want that sum to be close to the representation of the original word. So this is a little bit complicated way how to do it. You can do it even simpler way. So in 2014, there was this new approach where you just created all these windows. You just counted how often does this word is 10 words apart from this other word. You just counted the occurrences in this very large matrix. 10,000 on 10,000. It's not actually that large for today's standards. And then if you then compressed this matrix into 300 dimension, you did something like SVD, right? Then you suddenly got something like representations similar to this Word2Vec method. So we went from the high dimension into a smaller dense dimension, and we have for each word, we now have a list of numbers that represent the word. There were other methods, not only Word2Vec and GloVe, but also fast text and star space that came later, which also deal with embedding of the subwords, and star space is sort of even more general, that you can work with users and so on, but they have very similar approach. The problem with this approach is that there is no word disambiguation. We don't care what are the different meanings for the word. We just care about statistical meaning of the overall meaning of the word. If the word has multiple meanings, we can't deal with that. And what does it actually mean? Can we sort of represent this disambiguation clearly in computers? So we can do this using a knowledge graph, where, for example, each node, we can have 2 nodes in the knowledge graph. So that's a graph of all things, for example, it could be. And we can have an apple and pear, both are fruit. And they can have some relationships. So apple is subclass of fruit, pear is subclass of fruit. And then apple can have a color red, and pear can have a color red as well. And in this kind of space, we can have 2 nodes for apple. In one case, the apple could mean computer. In another case, the apple could mean fruit. Or we can have a fruit as a flowering, and we can have a fruit as a food. So in this sort of, we can represent these sort of different concepts with their relationships in this sort of database, which is called knowledge graph. And Wikipedia is, for example, something like this, where you can have articles which relate to each other, and you can have 2 articles with the same name, but they in the different contexts they mean different things. And if you think about it, if you actually random walk across this knowledge graph, you're actually forming sentences, right? You are basically saying apple is a subclass of a fruit, and fruit is also contains a pair. So you are sort of creating a valid sentences by walking across this knowledge graph. And if you took these sentences, you could actually create node embeddings using the Word2Vec for each of the nodes, right? And suddenly you would start forming embeddings for these words, and it's sort of this is supposed to help you a little bit to understand this ambiguation and this knowledge, introduce these knowledge graphs a little bit, and also think about what is a valid sentence and what it sort of can mean in this context of knowledge graphs. And that's where we get to the contextual word vectors, where you can see that there are some sort of valid sentences that make sense because they use words in a reasonable context, and we as a humans actually are able to disambiguate what is meant by the word in the context. Like we can understand if we mean fruit as a flowering or apple as a computer or not. And we can do that because of that we can see the surrounding words in this hypothetical knowledge graph, and we can sort of understand where we are moving within this knowledge graph, right? And how do we do this? We do this by understanding the context and locating ourselves in those concepts of the knowledge graph. And something like this can be reproduced a little bit in computers, where if we don't embed, in that case, we cannot just work with the word on its own and do just simple summing of the surrounding vectors, but instead we do something similar at the beginning. We embed all words into higher dimensions, but then we need to relate them to each other. And so we add these additional layers which interrelate them. And then at the end, it's some sort of neural network that could be, for example, transformer architecture or recurrent neural network. And then at the end, we may require the correct disambiguated word vector prediction. And so in this way, by providing the full context and having something more complicated, more complicated model, we can actually model different meaning from the same word given the context. So if we give context, the word can get the right meaning thanks to the contextual model. These sort of models have usually a context of hundreds of words, these transformers, and basically the surrounding vectors locate our position in the knowledge graph. And the transformer architecture is state of the art at this moment on many tasks. Okay, we spoke about the text. In case of images, we do something similar, and we can use as well the transformer architecture in that case as well. And how we can work with images, how we usually work with them, is that we split the image into some overlapping patches. For example, convolutional networks, not only transformers, but convolutional neural networks basically also work with overlapping patches. And in case of convolutional networks, they basically on each of these patches sort of use the same networks. They sort of ran them through similar things, and they keep for each position for each patch, they sort of keep the representation. They run it through similar networks. And so since the input is a two-dimensional square image, then the output is also a square, but in this case a matrix, right? So input is a square patches, and output is a square matrix as well. And then in convolutional neural networks, they progressively pool them, so because they do again another sort of overlapping tokenization patches on top of that. they then can they have sort of this pyramidal structure in the neural network, these convolutional networks like resonant. And for example, in case of transformers, in case of the vision transformer, we don't actually do this pooling so much. We have this transformer encoder, which again looks at all the patches, but it transforms them very similar to the way we work with the words, such that the output actually has the same it basically has the very similar. Let's say that it keeps dimensionality. The input is a sequence of patches, and output is also sequence of patch representations. So the sequence is of the same length and the dimensionality is the same within the network. And yes, and so basically this was about representations, about embeddings, where in case of the images we represented patches as a embedding in a sequence, and then made them contextual via this smarter, bigger network, via this transformer. In case of the words, we started with documents, counting words in the documents. Then we look at the word level, represented each word statistically with single vector, and then we got to this contextual representation where each word is represented by a vector, but based on the context it appears in. All right, I hope this was helpful. If you have any questions, let me know. I will be improving all of this every time, like adding new posts. So you can subscribe on Twitter, YouTube, and so on. And by email also, you can subscribe to a newsletter. And hope you like it. See you next time. Bye.